Okay, conservation of momentum examples. First example involves a cannonball in a cannon. Okay, so here's my sketch here. Cannonball in the cannon before, and then after firing, the cannonball moves to the east at 85 meters per second, and the cannon recoils. Okay, and so let's find out some stuff. First of all, we're given the mass of the cannon. Okay, we're given the mass of the ball, and we know the velocity of the ball. I'm going to designate east as the positive direction. Okay. Okay. First thing to find: what is the momentum of the cannonball system before firing? Well, momentum is given as p is equal to m times v, and before the firing, neither the cannonball nor the cannon are moving. Right? So we can say that there is no motion at all, and if there's no velocity, then there's no momentum. So p before, the momentum before the firing, is 0. Okay, what is the momentum of the cannonball after firing? Alright, if I represent the momentum of the ball as m times v, the mass of the ball is 5 kilograms and the velocity is 85 meters per second. So inserting those numbers, and I get a value of positive 425 kilogram meter per second. Or I could just as easily say 425 kilogram meter per second to the east. Okay, either answer is okay. Part C, what is the momentum of the cannon after firing? Okay, here's where conservation of momentum comes into play. Conservation of momentum says that the total vector momentum of a system remains constant. Okay, we can write that mathematically as this: p before is equal to p after. The boldface indicates the vector nature. All right, now we know that the momentum before is 0. We found that from part A. And p after is contained in both the ball and the cannon. Both objects are moving, so both of them have momentum. Okay, so the momentum after is the sum, the vector sum, of the ball's momentum and the cannon's momentum, which I will write as that. And we know that the momentum of the ball from part B is positive 425 kilogram meters per second. Okay, so now what I'm going to do is I'm going to insert those values into p before is equal to p after. Momentum before was 0. The momentum after was the momentum of the ball, positive 425, plus the momentum of the cannon. All right, and then we want to solve for the momentum of the cannon, which we can easily do by subtracting 425 from each side. Okay, and then we're left with the momentum of the cannon is equal to negative 425 kilogram meter per second. Or we could say, let me move this out of the way, as 425 kilogram meter per second to the west. All right, if the cannonball is moving to the east, the cannon moves to the west. All right, so we can see that the momentum of the ball of the cannon is the same as the momentum of the ball, but in the opposite direction. Okay, momentum of the cannon is 425 kilogram meter per second to the west, while the ball is 425 kilogram meter per second to the east. Okay. Finally, what is the velocity of the cannon after firing? Well, momentum is given as mass times velocity. We want to solve for the velocity of the cannon, which we can do by dividing out the mass. All right, and so we get this, and then inserting our values, and numbers work out kind of nicely to get negative 1.0 meters per second, or 1.0 meters per second to the west. Either answer is okay. All right, example number 2. We have a gun with a mass of 3 kilograms firing a bullet. Determine the recoil velocity of the gun. All right, which we can do. Here's my data table. Now remember, we need to convert grams to kilograms. All right, so 3 places to the left gives us this. Okay, now we're going to start with p before is equal to p after. That's pretty much our starting point with all these momentum conservation problems. Okay, now we can do this. I'm going to do this one of two. I'm going to do this 2 ways. Okay, first I'm going to figure out the the momentum before being 0 because the gun and the bullet are not moving before firing, and the momentum afterwards is the momentum of the bullet and the momentum of the gun, vector sum. Okay. All right, I'm going to find these individually. The momentum of the ball, momentum of the bullet is the mass of the bullet times its velocity. All right, and that's given right there, so we can insert our values, and I get positive 6.25 kilogram meter per second. Mass times velocity. Okay. The momentum of the gun is going to be also its mass times its velocity. We don't know what the velocity is. It's actually what we want to find, but I'm going to insert the value for the mass here. Okay. All right. So now I'm going to take these numbers and I'm going to put them in my expression here. So I get 0, p before, is equal to the momentum of the bullet plus the momentum of the gun. All right. And now I need to solve this algebraically for v sub g, which I can do by first subtracting out this term. I get that is equal to that, and then dividing out the 3 kilograms. Okay, and my answer, v sub g, is equal to this calculation, which turns out to be negative 2.1 meters per second. If the bullet moved to the right, which I designated, or in the positive direction, then the gun is going to recoil in the negative direction. Okay. All right. Now I'm going to do this problem again, but I'm not going to figure out the numbers in between. All I'm going to do is I'm going to start with p before is equal to p after. Okay. And I'm going to go from there. Now I know that the momentum before is 0, and the momentum afterwards is the momentum of the bullet and the momentum of the gun. The momentum of the bullet is its mass times its velocity. The momentum of the gun is its mass times velocity. I'm just going to insert these values into here right away, like this. There's the momentum of the bullet, there's the momentum of the gun. And I want to solve this expression for v sub g. All right? I'm going to use the same method that I did before. I'm going to subtract out this first term. I got to isolate the gun term first, and I can do that by getting rid of the bullet term. All right? I get this. Negative is equal to that. And now I'm going to divide out the mass of the gun. And I get this. Okay? V sub g is equal to negative m sub b v sub b over m sub g. All right? Now, I'm going to put my values in. A little cancellation later yields the same answer, negative 2.1 meters per second. Okay? I prefer this second method because I end up writing less and I only pick up the calculator once, less chance for error, but some people like to do it the first way I did it as well. Okay. Next example. I have a bowling ball hitting a pin. All right. All right. Given the data here, so I made a little sketch here. Okay. And all my stuff and my starting point, p before is equal to p after. All right. Now, before the collision, the momentum is the momentum of the ball and the momentum of the pin. Well, pin is stationary, right? So we can say that the momentum of the pin is 0, and that term drops out. All right. And the momentum of the pin the momentum of the ball is its mass times its velocity. Inserting those numbers, I get a value of p before as being positive 33.6. Okay. And I know that p before is equal to p after, right? So I know that the momentum after is equal to 33.6. All right, well, the momentum after is contained in both the ball and the pin because both of them are moving. All right. Now, I can find the momentum of the pin because I know its mass and I know its velocity. So I'll do that. Go ahead and plug in the mass times the velocity, and my calculator said this, positive 25.96. Okay. Well, now I'm going to plug these numbers in. I know what that p after is, and I know what the momentum of the pin is, so I can find the momentum of the ball. All right. Let me get this out of the way. And by subtraction, I get the momentum of the ball is this value. Okay. And then finally, I can find its velocity by p is equal to m times v. I know what its momentum is. I know what its mass is. so I can insert my values there. A little cancellation later. Gives me a value of positive 1.1 meters per second. So the ball is moving forward with a speed of 1.1 meter per second. Okay. All right. Well, now I'm going to do this problem again, but I'm going to use only letters. Okay. I'm not going to do it intermediate numbers. All right. So momentum before is equal to the momentum of the ball plus momentum of the pin. The momentum after is equal to the momentum of the ball plus the momentum of the pin. All right. Now, I do know that the pin before the collision has a momentum of 0. So that term's going to drop out. All right. I do insert zeros whenever they come up because that just makes terms drop out. The momentum of the ball before the collision is its mass times its velocity before the collision. The momentum of the ball after the collision is its mass times its velocity after the collision. The momentum of the pin is its mass times the velocity of the pin after the collision. Okay. Now, a lot of terms here, but only one of them is unknown, that which we want to find. Right? So I want to isolate this V1A term. Okay? All right. So here's how we're going to do that. I'm going to subtract out the second term, the pin term, and these do not combine, so I just have to write them like this, M1 V1B minus M2 V2A equals M1 V1A. Now I'm going to divide out the mass. And what I'm left with is this. Okay? Alright. Now I'm going to plug my numbers in from my data table, being careful to put them in the right place, and then picking up my calculator once, I get an answer of the same, positive 1.1 meters per second. Okay? Alright. Next example. Golf ball. Mass, blah, moving a blah, collides. So I have my little sketch here. Okay, golf ball hitting a baseball. The baseball moves forward at 12.9 meters per second. Golf ball, well, it might move backwards and might move forwards. I don't know. I guess this. Let's see how if I'm right. All right. Now, I know that P before is equal to P after. And I know that P after is equal to the vector sum of the golf ball and the baseball. Okay? P before is contained only in the golf ball because the baseball is not moving, right? So, I know that P before is equal to P1B, that's the golf ball, plus 0, that's the baseball. All right, now, those of you who like to do this by calculating the numbers as we go, just pause this for a moment and find the momentum before the collision. That is, find P before. And you can get that by finding the momentum of the golf ball. So pause that, and then I'll show you the answer in a moment. Okay, what we get is this. Hopefully you got that value. All right. Now, what I'm going to go after is the momentum of the baseball after the collision. Okay, so again, pause this, find the momentum of the baseball after the collision. And I get this value. Okay. All right, now, take these numbers now, put that in for P before, put that in for this, and find the momentum of the golf ball after the collision. Pause, and I'll give you the answer in a moment. What we get is this, negative 0.675. I subtracted this from each side. Okay. Then finally, since the momentum of the golf ball is equal to its mass times its velocity, pause this and find its velocity. And our answer is negative 15 meters per second. Okay? Okay, those of you mathematical people, or the ones who only want to pick up their calculator once, we can do this again, like this. P before is equal to the momentum of the golf ball plus the momentum of the baseball, After the collision, likewise. Okay. I know that the baseball is stationary, so I'll put my 0 term in there. Momentum of the golf ball is equal to its mass times its velocity before the collision. After the collision, the momentum of the golf ball is equal to m1 v1a. The momentum of the baseball is m2 v2a. Our unknown is v1a. So we want to solve for this term. Let's get rid of this, subtract it out. m1 v1b minus m2 v2a equals this. Divide. Put your numbers in. Careful to put them in the correct place. And your answer ends up being, as you might expect, negative 15 meters per second. Okay. Those are examples of elastic collisions with the golf ball and the baseball and stuff. Now there's another type of collision that's called an inelastic collision, and that's when things stick together. And a typical physics example that we use are train cars that couple together after they collide. Okay, so here's one. Train car, blah, 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 couple together and move down the track with velocity v. Actually, VA. Should make that consistent. Oh, well, sorry. And so we want that. All right, so P before is equal to P after, just like usual. And now I can say that P before is contained in the momentum of this first train car plus momentum of the second train car. The momentum after is the momentum of the coupled cars after they're stuck together. All right. Now, the second car isn't moving, so I can drop out this second term before the collision. And the momentum of the first car is equal to its mass times its velocity. So m1 times v1b is equal to the momentum after the collision. Now, v sub a, that's its velocity. Cap m is the mass of the cars after they're coupled together. And I can find that mass by simply massing the individual masses, summing the individual masses, sorry, to get 3,200 kilograms. All right. All right. Now we can solve for the velocity by dividing out the mass. And I get this. And then plugging in my numbers, the answer turns out to be 1.6 meters per second. Positive, actually, since they move down the track in the positive direction. Okay. Okay. Last example. Running back is getting hit by a linebacker. Okay, so got some images here. There's my running back moving at that velocity, linebacker moving at that velocity. Okay, after they stick together, inelastic collision, they're going to stick together, and I just ended up summing their masses right away. All right, and what I want is the velocity of this system, the two guys coupled together, after the collision, stuck together. All right, P before is equal to P after. All right. Now, before the collision, we have both guys moving, right? So this guy's moving, this guy's moving. And then the momentum after the collision is their combined masses. All right. Now, if you want to stop and find out the individual numbers and then plug these in, and to find the momentum, do it that way. Fine. Go ahead and pause it and come back. I'm just going to insert the values. So and when I say values, I mean variables. So the momentum of the running back before the collision is his mass times his velocity. The momentum of the linebacker is his mass times his velocity. After the collision, it's their combined masses times the velocity after the collision. That's what I'm after. That's what I'm going for. All right. So I'm going to just divide out this big cap M. Get rid of it. All right. And what I'm left with is this. And then by plugging all my numbers in, okay, I find out that my answer is positive 1.1 meters per second. So these two guys, they end up moving to the right at positive 1.1 meter per second after the collision.